Welcome to the deep dive. Our mission, as always, is taking complex engineering sources and, well, pulling out the key insights you need. Clarity and momentum, that's the goal. Today, we're diving into something really fundamental. The absolute necessity of solid software architecture. We're looking at system building, really, and we're starting with that great quote. To build, that is the noblest art of all the arts. It sets the stage perfectly. We're treating software not just as coding, but as a true architectural challenge. And the big question we're tackling is, if architecture is the answer, what exactly was the question?
Right, and we've kind of broken that down using what the source calls Baker's dozen 13 reasons, basically, some technical, some not. And these points are super useful, whether you're, say, justifying resources for a new project or analyzing an existing system, or maybe even thinking about how to evolve it.
Okay, and we're jumping straight into what you said is the most crucial lesson, the cornerstone, really. That's the link between architecture and system quality attributes. Let's unpack this.
Yeah, number one, the absolute foundation. Architecture either inhibits or enables your system's quality attributes. If you take just one thing away today, let it be this. Your system's ability to hit its targets for performance or security or modifiability, it's substantially determined by the architecture. You can't just add it on later. It doesn't work that way.
Okay, so if I say, I need high performance, what architectural levers do I pull? It's not just faster chip.
Definitely not. I mean, hardware helps, but architecture is key. High performance means architecting how you manage time-based behavior. It's about how shared resources get used, controlling the frequency, the volume of communication between different parts of the system. If everything is constantly chattering back and forth, performance tanks. It doesn't matter how fast your hardware is.
Okay.
And it's the same idea for other qualities. You want high modifiability. The architecture needs to assign responsibilities clearly and, crucially, limit the coupling.
The
Yeah.
interconnectedness.
Exactly, how tied together things are. You want it loose, so ideally, a change only affects one small piece,
Yeah.
one element.
And security. How does architecture approach that?
Well, security is heavily architectural. You design in things like a strong perimeter. You manage and protect communication pathways. You might include specialized elements, like specific authorization checks or firewalls, right into the system structure from the start. For scalability, it's about localizing resource use, avoiding hard-coded assumptions. That makes it easier later to swap in bigger components or just replicate parts.
That ability to manage change, that seems like where the real economic value kicks in, especially after deployment. And change is always happening, isn't it?
That brings us straight to reason two. Reasoning about and managing change. Yet change is the norm. It's not the exception. Data shows something like 80% of a system's total cost happens after launch. Maintenance, new features, bug fixes. If you don't manage that effectively through architecture, you're just piling up a technical debt fast. Architecture helps because it lets you think about change in sort of three buckets. This is really important for planning. First, you've got local change. That's the dream, right?
Mm-hmm.
You modify just one single element, like add in a new rule to just the pricing module. Simple, clean.
Okay, that's the ideal.
Then there's non-local change. This needs changes in multiple places, maybe add a rule, update some database fields, tweak the UI. But the key is the underlying architecture, the structure. It stays the same.
Right. More work, but manageable. And then the scary one, architectural change. When does it cross that line?
Good question. It crosses the line when the change hits the fundamental ways elements interact, the core assumptions, like deciding to go from single-threaded to multi-threaded, or changing your main communication protocol between major parts. That's not just tweaking elements, it's changing the blueprint. High risk, high cost. Often means rethinking huge chunks of the system.
And if you don't maintain that sort of conceptual integrity, the source calls it architecture debt. What does that actually look like in practice? Is it like financial debt?
It's a really good analogy, actually. It's like taking out a high-interest loan. You make a quick fix now that violates the design principles. Maybe you tightly couple two things that shouldn't be linked just to get a feature out the door.
Okay.
You solve today's problem? Maybe. But you make every future change harder, more expensive, more prone to breaking things. The interest you pay is in extra developer time, more bugs, slower delivery down the road. So yeah, sticking to the architecture, it's just smart financial management for the project.
That ability to categorize and manage change then feeds into reason three, predicting system qualities.
Exactly. Because we know certain architectural choices lead to certain outcomes, we don't have to wait until testing to find problems. We avoid that whole painful cycle. Design, build, test, oops, now start hacking fixes in. If we know, for example, that a specific layered pattern helps modifiability, we can predict that early. We can analyze the structure, even just on paper or in a model, spot potential performance issues, security gaps before writing tons of code. Saves a massive amount of rework.
Okay, let's shift gears a bit to the people side of things. Reason 4, communication among stakeholders. Architecture as a common language.
Precisely. It's like a shared map,
Yeah.
a simplified model that everyone involved can point to and hopefully agree on. Think about all the different people, users. They want speed, reliability, customers. They're worried about budget, schedule, managers. Team assignments, maybe independence between teams. Developers need to know how things actually work together. The architect worries about the strategies to meet all those goals. The architecture description, the diagrams, the documents, they become the common ground for all these groups to talk, negotiate, and build consensus.
The source material has this great story about a big government project review. The architect shows a simple box and line diagram.
Yeah, the mode select button anecdote. It's fantastic. A non-technical person looking at this abstract diagram asks a really basic question. What happens when you push this button?
Simple question, big consequences.
Huge. That one question, prompted by the abstract architectural view, revealed they'd completely missed defining a critical piece of behavior. It sparked this long debate, clarifying requirements nobody had caught before. It just shows the power of even abstract views. They can trigger exactly the right conversations, especially with non-technical stakeholders, to nail down what the system needs to do.
And that conversation works because architecture embodies reason 5, early design decisions. These are the first ones made, the most fundamental and, crucially, the hardest to change later.
Absolutely. These decisions basically define the system's DNA. Single processor or multiple. How many layers in the software stack? Synchronous communication or asynchronous? What kind of encryption is baseline? Operating system choices, maybe. Communication protocols. Once you bake those into the architecture, trying to change them later, it causes this massive ripple effect. It's like trying to change the foundation of a house after it's built. Very painful, very expensive.
And those decisions then enforce reason 6, constraints on implementation. Architecture sets the rules of the game for developers.
Exactly. It says these are the required elements, this is how they talk to each other, and these are their specific jobs, their responsibilities. The classic example given is performance budgeting. The architect sets an overall goal. Say, a transaction must finish in 200 milliseconds. Then, they break that total budget down. Assign smaller, specific budgets to the different parts. Maybe 15 milliseconds for this database call, 50 for that business logic step, and so on. The individual implementers, they just need to make sure their piece meets its specific, constrained budget. The architecture enforces that discipline, ensuring the overall goal is met. It's not guesswork.
This leads right into reason 7, influence on organizational structure. The idea that the software structure gets kind of engraved onto the project team structure.
Yes, and this is a huge non-technical impact. The architecture often directly shapes the work breakdown structure, the WBS. That's how the work gets divided up among teams. Got 5 major components in your architecture. You'll probably end up with 5 teams, each responsible for one.
Right.
And that WBS then dictates everything. Planning, scheduling, budgeting, who talks to whom, configuration management, the works. Once you set up teams around an architecture, trying to change that architecture later becomes incredibly disruptive and costly, just from a management and business perspective, even if it's technically the right thing to do.
Let's talk about project efficiency. Reason 8, enabling incremental development.
Right. Once you have that architectural blueprint, you don't have to build everything all at once in a big bang. You can start with what's called a skeletal system. This has the essential plumbing, the core infrastructure, things like initialization, basic communication paths, error handling, but very little actual application logic yet.
This sounds a lot like modern practices, like the walking skeleton idea or building an MVP, a minimum viable product. It's about tackling risk early.
Exactly. You build the infrastructure first, make sure it runs, make sure the core architectural ideas actually work. You validate the riskiest parts, the communication, the resource handling early on. You see this with things like extensions for platforms, say Visual Studio Code or maybe the R language. You build the shell, the architectural framework, before filling in all the features. It dramatically lowers the risk of finding a major architectural flaw late in the game.
Reason 9 feels related. Cost and schedule estimates. Good estimates need that architectural structure.
They absolutely do. The best, most reliable estimates usually come from a sort of negotiation. You have top-down estimates, maybe from the architect or project manager, based on the overall size and complexity defined by the architecture. And you have bottom-up estimates from the developers who are actually building the individual pieces. They know the details.
So you need both perspectives.
Yes. The process of comparing those, discussing the differences, and reaching a consensus, that usually produces a much more realistic schedule and budget than either top-down or bottom-up alone.
Now let's talk reuse, big leverage here. Reason 10. Architecture as a transferable, reusable model, especially for product lines.
Oh yeah, the payoff here can be massive, orders of magnitude sometimes. A product line is basically a family of related systems. They share a common base, common assets. The architecture is the key. It defines what's fixed across all products in the family, the core structure, the essential components. And it defines what's variable, the parts that can be swapped out or configured differently for specific products. Once you have that solid product line architecture, building the next product in the family becomes way faster, cheaper, and often higher quality because you're reusing proven parts. Huge business advantage.
And Reason 11 builds on this idea of using existing parts. Architecture allows incorporation of independently developed elements, moving from pure creation to assembly.
Right, we're not always writing every single line of code from scratch anymore.
Yeah.
We're often assembling systems from existing pieces, things like CO&AS commercial off-the-shelf software,
Hmm.
or open source libraries,
Hmm.
or maybe services running elsewhere on a network.
So the architecture defines how these external pieces plug in.
Exactly. It sets the rules they have to follow, how they interact, the data formats, the protocols, rigid constraints, the benefits, faster time to market, lower cost, often better reliability too, because those COTS parts or open source libraries have usually been tested and debugged by lots of other users already. This whole approach is enabled by the idea of open systems defining standards so components can interoperate and you avoid getting locked into a single vendor.
Okay, final stretch. 2 more reasons, focusing on discipline and training. Reason 12 is restricting the vocabulary of design alternatives. This sounds like limiting creativity.
It might sound that way, but it's really about engineering discipline, so voluntary restriction. Experienced engineers don't usually chase novelty just for kicks. They tend to stick to a smaller set of proven solutions. Established architectural patterns, known tactics, things that work.
So it's about predictability.
Yes, it's risk mitigation. By intentionally limiting your design choices, you make the system simpler. You boost reuse, analysis becomes easier, interoperability improves. Ultimately, you get more predictable, successful outcomes. Brand new, unprecedented designs are exciting, maybe, but they're also inherently riskier. Discipline pays off.
And finally, reason 13, a basis for training. Architecture as the entry point for new team members.
Absolutely. When someone new joins a project, where do they start? The architecture documents are often the first best overview of the entire system, and different architectural views help different aspects of training. Module views, for instance, show the static structure. What are the pieces? What are they responsible for? Critically, which team owns which module?
Right, who do I talk to about this part?
Exactly. Then component and connector views, they show the runtime behavior. How does the system actually work? How do the pieces interact to get the job done? And allocation views show how the software maps onto the environment, like which components run on which servers in the deployment setup, or how source code maps to development teams. It's the complete picture.
Wow, okay, that was a comprehensive list. Let's recap quickly. Architecture enables quality, manages change, allows prediction, helps communication, holds early decisions, sets constraints, shapes the organization, allows incremental building, anchors estimates, enables product lines, supports assembly, restricts design choices, and provides a basis for training. 13 big reasons.
So what's the bottom line here for you, the listener? It boils down to this. The architecture isn't just some diagram you draw at the end. It's not optional. It's the central foundational artifact. It drives technical success, how the team is organized, how the project is planned, and the long-term costs. It fundamentally determines if your system will actually meet its goals.
And if you remember nothing else from this deep dive today, remember that first reason. The question architecture really answers is, can the system achieve the quality attributes it needs? Performance, security, modifiability. Architecture is what substantially determines that outcome. If you shortchange architecture, you're basically guaranteeing problems down the line. Thank you for joining us for this deep dive into why software architecture is so critically important. We hope this gives you a solid understanding of why building with architectural integrity really is, well, the noblest art. We'll catch you next time.